you guys to do right now is draw a potential well for a harmonic oscillator. Okay, that's number one. Number two, how many of you guys remember when we're talking about diatomic molecule, the potential energy as you forming bonds? We call the force potential, 612 potential. Or you guys draw potential between two atoms. So let's draw two potentials. One is the harmonic oscillator potential. The other one sketch a potential energy for a molecule, diatomic molecule. Does that make sense? Have you guys never exposed to a potential energy for a molecule? Okay, then I'll show you one. But sketch it right now. So as an object attached to the spring attached to the ball using classic physics, then the restoring force is proportional to the displacement with a constant of spring constant. If the force is satisfied with the Hooke's law, then we define this as a simple harmonic. Of course, you can have other kinds of relationship. Under that circumstances, then we can derive the potential energy. So it's a parabolic, right? So you can look at the middle is your equilibrium position, and then you have extension, and then you have compression, okay, to the spring. Now, if you're thinking about the molecules, right? Let's say I have a molecule HCl. So you have H atom, Cl atom, right? Now, if you can imagine the interaction, so you can consider the distance between those two atoms using R or X or whatever you would like to, or D. Now, can we imagine you have two atoms that are very far apart and starting moving really close? At one point, they reach to the favorite position, favorite energy. What happens? They form bond. Okay. Now you keep pressing or making the distance closer than the bond, and you can imagine in those three different regions. So you have hydrogen, Cl, very far apart. What do you think about the interaction?
Well, the chlorine's gonna hog most of the hydrogen's electron because it's like the second most electronegative element.
Oh, okay.
Right?
Then let's make it simpler. Let's make it H2. All right. Let's start with simple. Okay.
I do have a question about the electronegativity.
Yeah.
We'll get to that later.
So we can come back to this one. All right. So let's think about hydrogen. Two hydrogen atoms. Let's start it with this because you guys haven't heard about it, so let's don't jump too far. So very far apart, what happened? Think about me. I'm here with you guys in engineering beauty and chemistry beauty. We don't see much of interaction, so it's 0. As I'm getting closer and closer, what happens? You feel the interaction, and that is attractive. If it's an attractive interaction, the energy will have a positive or negative sign.
Positive.
If it's attractive interaction.
Positive.
We have two types, right? Repulsive and attractive. So one is positive, the other one has negative sign. The attractive has a negative sign. So then as you're getting closer, the attractive force will increases, and to the point you feel the repulsion as you're getting closer, as you're forming the bond length, it reaches to the equilibrium. So therefore, if I want to draw, it's called a Leonard-Jones, or Morse potential, or we call the 612 potential. If I draw this on the board, I think you might feel familiar with this. All right, so at far distance, Jones, I can write it out. Or we call it Morse potential, or we call it 612 potential curve. All right, they are referring to the same. Now the reason they have this, sorry, this is R. I use the E and the X and D and the L to refer, that just refer the distance between those two atoms, okay? Now, the 6 and 12 is really referred to the relationship between those two types of interaction. See, the term, this is a positive term that indicates the repulsion, because those two atoms can experience attractive and repulsive interaction. So this is to the distance raised to the power of 12. And this is a negative term that indicates the attractive interactions. And then you can see it's a function of the distance, so the attractiveness is more predominant at this distance reach to the equilibrium, and then you have the repulsive component. Now the reason I'm showing this for you, so basically, I should have made it more of this is 0. I think this curve, if I draw it, intended to draw it, should be like this, right? So because very far apart, there's no interaction, it should be 0. As you're getting closer to some point, you feel that it's attractive, predominant, then reach to the balance at the equivalence point, and then you press over that, then the repulsion dominates. Okay, so this is what we usually use to describe the interactions between two atoms in a molecule. Now, in chemistry, we have this also 0 here. What is that? That is the distance between the two atoms. At some point, it will form a bond. Very far apart, no interaction, no bond formation, as getting closer and closer. So at this point, position, the distance, it is really the in black, the bond length. That is your bond length. Okay. So after I draw this, you guys still haven't seen that yet in your gym kit?
No.
Oh, okay, I can see this part. You don't really, we usually touch it, but that part. Okay, now the reason that I'm touch bases with you, now you can imagine the bond is a spring. So we can think about vibrational motion, right? The vibrational motion, you have a stretch between those two atoms. Now, can you look at this parabolic potential energy with respect to the position versus this Jones curve? They are similar in some aspect. They are very similar. So as a harmonic oscillator, if we think it is a harmonic oscillator, then it is symmetric with respect to the equivalent position, right? It's a parabolic. Now, for our real diatomic molecules, if we consider the bond is your spring, then this is a real potential energy curve. It is not exactly the same. However, if our system or molecules for those two atoms is around the bond length region, then what do we see? It is also looking like what? Symmetric and parabolic. So therefore, we can use this simple harmonic oscillator model to model diatomic molecules under the constraint if we consider the system within the equivalent position, within that range. Because if you look at here, that's not the same as this potential energy curve. Does that make sense to you guys? Okay, all right, so now that's the whole point. If you don't know, now we're gonna see this all the time, this potential energy curve all the time. Now I'll give you some mathematical curve equation here, since I know I have this idea, but I'm not gonna ask you guys to write it on the exam or anything, but that helps you understand this potential energy curve has an attractive and repulsion component. Okay, so now let's touch bases with our application. So we learned the harmonic oscillator. Now what do we do? The one thing is to understand the vibrational motion for molecules. As usual, when we touch bases with something new, we start with something really simple. So you could have diatomic molecules, have a string, or you could have polyatomic molecules. So we will start with a diatomic molecule. Then we will extrapolate or for you guys to self-study and go from there. Okay, if you look at, I show you the energy differences, but we will touch bases at this region so we can use that model. Now the other thing that is different for the harmonic oscillator, you can think about this system for the simple harmonic. You have an oscillator attached to the spring, then the spring attached to something infinity on the wall. But in the diatomic molecules, you have two atoms attached to the spring. So therefore, we need to make an adjustment to the mass right now. Does that make sense? Even though you have two atoms, how are we going to calculate the mass of that oscillator? Because in the simple harmonic, we have a mass of M as the oscillator. But here, it's a diatomic. Now, how are we going to generate the mass expression? Okay, now that's the change. So what we're going to do is we are going to use the effective mass. That part, you guys learned this in physics? Effective mass? Yes.
A little bit.
Okay.
I think a little bit.
So the effective mass is really evaluate the degree which mass contribute more to the vibration here. Okay, now if you guys have a learner or your learner, I'm just giving you the expression right here. So you use the simple and of course we know, refer to mass. We use EFF to refer to as your effective mass. Now in this system, you have 2 points. You have one atom mass, the other atom mass. How can you calculate the overall effective mass for that as an oscillation, for the oscillator? Then this equals to, okay, the mass for the atom 1 times the mass for the atom 2. So the product of those 2 point mass divided by the sum. All right, so as I said, this is really to evaluate which contribute more to the vibration. Let's give it a try, right? I mean, they said this have 2 because the bond, you have one, you have another one, and then you have a spring, and this is really your bond. Both can be subjective to the vibration. Now, how can we think about it as overall mass? Then we can use the effective mass to evaluate using this particular equation. Now, I said this can tell us the evaluation, right? So let's say, what if I have hydrogen atom here, Cl atom here? Now, can we calculate the effective mass? All right. So let's give it a shot. So the effective mass in this particular system, equal HCl. Alright, now what is the mass for a single hydrogen atom? mole of hydrogen equals to
1 gram. So then you divide
1 gram, right? So 1 gram, then I need to convert it to what? Oh, you know, I think in the US, we have this tables from one unit go to the other unit. All right. Let's do this together. I'll take some time. So it's a 1 gram per mole, or it is 1 times 10 to the negative 3 kilogram per mole. You guys agree with that? Okay, but I'm calculating a single atom. That is a 1 mole atom. So I can divide it by Avogadro's constant to get the mass for the single atom, which is
6.626 times 10 to the negative 32nd. That's 23rd, sorry.
what? Did I get Avogadro's constant? Okay, I'm checking on you. What would be the value?
cancel.
I don't know Avogadro's constant.
Yeah,
Believe so.
that's good.
Wait,
That's not.
Oh, isn't it negative 23rd?
No.
No.
My bad.
No. Is that Avogadro's constant? I told you when I
Yes.
used to go to the exam, I only have 1 pencil, 1 eraser.
I
So
think
therefore,
so.
all the numbers, I'm just filled out all the things, right? So, but if it's not true, then let me know. That is what? Atom
Per mole.
per mole. Very good. That's how I think about it. I'm just teaching you how I think about it to calculate. You guys have a different ways of converting, that's perfectly fine. Okay, so that is just a mass for what? For the hydrogen atom with the mass 1, if I would like to. Now, how about the chlorine then?
35.
So it is 35.5.
4 or 5.
4, 5, I'm gonna go with 5. I'm just gonna write the Avogadro's constant, that equivalent to 6.02. So this is really your Avogadro's constant right here. Okay. All right, now what I'm gonna have? Divided by, this is your mass of hydrogen. This is your mass of chlorine atom. So this will be your mass of hydrogen plus mass of chlorine. So I don't have to write out the whole thing. Is that looking good? Okay, now mathematically, I can plug all the numbers and then get like accurate values. But I also can evaluate a little bit if I want to just approximate. What do you think about the mass of hydrogen with respect to the chlorine?
Negligible.
Pretty
Pretty small. Pretty small. So I could just say this whole thing I'll be approximated by what? The mass of chlorine. Right? Alright, then look at this. This is the mass of what? Chlorine divided by mass of chlorine. Now, in the exam, I don't want you guys just cancel out and give me approximation, but right now I want to make a point. So this will be canceling out. Then the effective mass equals approximated now you guys gonna get a very accurate value in the exam. I will ask you guys get a very accurate value, but with the approximation. Are you guys all on board with this? No?
How can you cancel? You're adding on the bottom.
Product. And the sum. But the
Yeah.
mass of hydrogen is so light with the chlorine. So you can approximate the denominator with the mass of chlorine.
Okay.
Then chlorine cancel out. You have mass of hydrogen. of the atom that contribute to the mass of this atom contribute to the vibration. So what do you guys think about this? So mostly it's coming from where? The hydrogen atom.
Hydrogen.
Although you have two atoms right there, because the mass of chlorine is so big compared with hydrogen, you can approximate the chlorine as a stationary, and the hydrogen is mostly contribute to the vibration. Are you guys following me okay? So that's an extrapolation from one mass caustic system. Now I have one mass, now I have a 2-point mass. I'm going to calculate, extrapolate with everything. Okay, now what about for H2? Then it has, what about H2 then for the effective mass? That would be 1/2 what? The mass of hydrogen. So they contribute equally. Okay, all right, so that touch bases. To borrow that simple harmonic oscillator model, we need to figure out how I'm going to calculate the mass on 1-point mass versus 2-point mass. On 2-point mass, we're going to introduce the effective mass. Okay, that's about it. All right, now I showed you here, we're going to make what we want to do using, why can't we use a simple harmonic oscillator is the most of the time, if you look at the most potential for the diatomic molecule along the equivalence position, they can be similar. So therefore, we can use that model to introduce the vibration motion for diatomic molecules. All right, in that case, how are we going to understand quantum mechanics perspective to this vibration motion for diatomic molecule? Then the idea is the same. We need to come up with potential energy that is the same as your the potential energy for the harmonic oscillator, since we're considering near the equivalent position. And then you will have the kinetic energy term. I think the only thing that is different here is do the same, because that would be a good model for us at the equivalence position. Now, the kinetic energy, if it is that's the operator, but that's only for the 1-point mass. Now we have a diatomic molecule, so we need to make change. How are we going to change? Instead of single mass, now we're going to replace this mass with effective mass. You can either use effective mass or use this U as a symbol. Now this is the extrapolation. Okay, in that regard, we can solve it for the solving for the Schrödinger equation. As you guys can tell, the solution will be exactly the same as this simple harmonic oscillator. The only changes is the mass will be replaced by this effective mass. Okay, now we already have all the energy values. I'm just bring here again, just applying to what we have for the simple harmonic to the diatomic molecules, except that we needed to use the effective mass. That's about it. All right. Now, the idea, a new idea, we're talking about the vibrational motion. We use vibrational terms. All right. We can express the energy in terms of the quantum state. So our solution would be exactly the same, right? Because since we use the same model and everything the same. And then we can, instead of using the angular frequency, we can use the normal frequency. So this will become the V plus 1/2. Then you have H here. Alright, the V here is the quantum number that we learned, which is this guy here. It's a vibrational quantum number. Right, what about this guy here, guys? That is the normal frequency for
Oscillator
for the oscillator. Yes, or in this case, your for the molecule, for this diatonic molecule. Alright, this is so far what we have learned in our previous lecture. But we can substitute the frequency with wave number. So what is the relationship between frequency and wave number? This is the wave number, right? Wave number is it the inverse of wavelength? Okay, all right, so therefore I can continue to write this in terms of angular frequency, in terms of the frequency, and then you can write in terms of the wave number. Now, I don't know how many of you guys still remember. I want to try me one more step. For the harmonic oscillator, the frequency for the oscillator equals to the frequency of the light. I think I derived it all the way here in the Friday lecture. You guys remember this? The frequency of the oscillator equals the frequency of the light, and the frequency of the light can be substituted with the C time, the wave number. So therefore, I can rewrite this energy expression from many different ways, but they are all linked together. Okay. Now, in the spectroscopy, the energy can be expressed in vibrational terms, which we use the G right here. All right. So we can define this allows you, I give you the expression in so many different ways of doing that. This allows you, if any of you are taking the spectroscopy class, you may think about the energy for vibration written in terms of the vibrational term. But this is really nothing fancy, because we started with the harmonic oscillator. We know the expression, then we can convert it to the normal frequency, convert it to the wave number, then we can substitute the vibration term in terms of the quantum number plus 1/2 times your wave number. That's about it. There's really no reason. It's just that's the definition. Okay. All right. How many of you are taking like advanced spectroscopy in your field and in chemistry? If you have done it, you probably would see a chart like this. Alrighty, but it's all started from our model, and then we can extend the expression. Okay, Now, we can have a sample problem. Determine the value for vibration energy, separation for a diatomic molecule. The force constant for the bond is -16.3 Newton per meter. Force constant, it is really your spring constant. Okay, the force constant for the bond. The bond is a spring, so that tells you the K value. So consider the bond. How are we going to do that? How are we going to determine the value for